Okay, everybody, welcome back to Math 365 PD. Nice to see you. I want to pick sort of right up where we left off last time at this so-called Huygens principle for the 1D wave equation, which really amounts to kind of analyzing D'Alembert's solution and just seeing where the function is going to vanish or not, depending on where the initial data is supported. So the situation is we have this initial data for the wave equation, and we have this assumption that we're going to make, which is that the support of H and G is contained in a closed bounded interval. And say that you've solved the wave equation in that circumstance. Let me try to fix the lighting a little bit. It's really all or nothing. Okay. That's fine. Okay, and so last time I drew this picture for you. In the xt plane. And remember, support is the closure of the set of values where the function is non-zero. So more to the point is that if you're outside the support, then the function must be zero, like outside of that. Not only must the function be zero, but at the point, there's also like an interval around the point where the function has to be zero. So that was the point of those technical definitions last time. And so you've got some interval where your initial condition is non-zero, and it's definitely, or at least you know it's definitely zero outside of that interval. And so I drew this picture. Where these are the lines B plus CT. And A plus CT, and correspondingly B minus CT, A minus CT. So in the space-time diagram, the diagram with time being graphed, looks like these 45-degree angles. I'm drawing it with C equals 1, even though C could be something else. But you know that physically looking at the string, you're starting with a wave, and it's kind of traveling to the left and to the right. That's the Gx plus CT, the Gx minus CT. But in space-time, you're kind of going off in that direction. But you can think of it, this is your wave that's traveling to the right, that's your wave that's traveling to the left. And if you're outside this region, then you're going to be zero. More on that in a second. But for now, I want to give you a class exercise. So we talked about these characteristic coordinates, namely, so let's take C equals X minus CT, and tau equals X plus CT. I think this picture is a little bit easier to understand than characteristic coordinates. And so your first class exercise is to please draw this picture again, but with the Xi tau coordinates. So in other words, draw the picture again, but on the coordinate axis indicated. Give you a couple minutes to work. Yeah, it is a rotation. That's true. So yeah, the question was kind of like, isn't it a rotation? And it totally is. It'll look like a 45-degree rotation, but do work out the equations and draw, those lines on this, on those axes with everything labeled. Okay, giving you some time to think, the first thing I'm interested in is what's the line, what's this vertical line? So what's the line given by t equals 0? You can reason it out by plugging in t equals 0 to those equations, finding out that c and tau are both equal to x and therefore equal to each other. So this initial line now looks like that. So t equals 0 or c equals tau. A and B are, of course, points on that line. And when you look at the, oh yes, let's finish drawing the diagram. So B plus CT. Well, this is really, it's the line X equals B plus CT, isn't it? And so that's telling you that constant B is equal to X minus CT. So this is the line given by C equals to B. So it's that horizontal line in this plane. And similarly equal to A. And now here we have X is like A minus CT. So constant A is equal to X plus CT, so A is equal to tau. So I'm getting now this vertical line. And also B is equal to tau, giving me that vertical line. So on the entire plane, you get these two horizontal strips, but of course we're issuing from our initial condition, and our initial condition is really this horizontal line. And so now you can see this is in the picture, it's just been rotated 45-degree angle. But that is the coordinate change, and now here are the coordinates. So you remember that D'Alembert's solution, function g, was written in terms of x minus ct, x plus ct. In fact, the solution in these coordinates is something like what? Like you see tau has to be what? 1/2 of g, just by direct substitution. I've got like a lot more space in the board here, but I've run out of the board on the camera. So g, c plus this integral. from C to tau each of us ds. So it kind of works out quite nicely in the Xi and tau coordinates. And when you say that G is supported on the interval from A to B, so then you're really looking at like when is the solution 0 or not 0? And the solution is like G of x minus CT or G of x plus CT. So
Does the other end of that bracket close after the G of C?
yeah, 1/2 of the G's plus the integral. Thank you. And that's all equal to the solution written in terms of the new coordinates. And so I can basically say that for G to have a chance of being non-zero, then you need, what do you need? Like x minus CT has to be between A and B. And same with x plus CT, which is the same thing as saying that tau is just between A and B. And so is Xi. So the part where the place where G of tau can be non-zero, that's basically in this strip. So this is your wave traveling in one direction. And the place where Xi can be non-zero is basically in this strip. If tau is outside of that range, G is 0. So now that's completely transparent. Maybe it was transparent before, but now it's absolutely clear. Here's the part where tau is between A and B. If you're outside that part, the function's 0. Similarly, here's where Xi is between A and B. If you're outside that part, function is equal to 0. Telling you that if you're in this region, then your function is actually, since this part is 0, your function is actually equal to 1/2 1/2C times this integral. But this is actually equal to nothing but integral from A to B. And the reason for that is this is precisely the interval where tau is bigger than B, and Xi is less than A. And since you know that the function is 0 outside of that interval, these two things are the same. And in particular, this means that this function is constant in that region. So you've got traveling waves, and then the function is constant in the middle. So I won't try to redraw the picture that's in your textbook. That's already very nice. But when you look at any of these solutions to the 1D wave equation using D'Alembert, and you see the two waves just running away in different directions, and with the extra energy bump from the initial velocity, then in the space-time diagram, you can kind of see them traveling off to the side, and in the middle, it settles down to 0. And going back to the other coordinate system, it's just exactly what I said last time. So I thought that would be a nice sort of treat to maybe explain that principle. It's not so bad, and remind us that, the mechanics of changing coordinates. Yeah, so now I want to dive straight into this idea of how do you solve the wave equation with fixed endpoints? So this is now really more like plucking a guitar string or something like that. We're keeping both the endpoints fixed for all time and the initial velocities fixed for all time. And so the physical model is the guitar string, but how you write this in space-time looks kind of like this. So I'm writing down the space-time diagram with t going up now instead of x. So imagine a string of length L with fixed endpoints, and you're trying to solve a PDE on the following domain. And so that really is the domain. You know, you're solving a PDE, uxt, on a two-dimensional domain. Time is one of the variables. And then the closure of that domain, minus its interior, is the boundary. So the boundary is here. It's this infinite rectangular region. So you need boundary conditions on that entire region. And so like before, you can take these, but this now gives you boundary conditions like just in this part only. So what about that part? So this is going forward in time. And in particular, you want to hold the string in the same position in time. And of course, it's not going to have any motion, and therefore its derivative will be 0 as you change in time too. And so how to write that down, you would just say, that the endpoints are fixed. So when x is equal to 0 and going up all the time, that's this part. X is equal to L and going up all the time, that's that part. So this is 0, and that's a consequence. And there are some compatibility conditions here. So these two things are incompatible unless it happens to be true that g of 0 equals g of L equals 0, and same way for h. And that's definitely physically realistic. You're just holding the string in place as you're plucking it. The guitar holds it in place, perhaps. And so these are kind of what I would call compatibility conditions implied by the boundary conditions of the PDE. And I'll tell you in advance, the strategy for solving this, at least right now, is pretty good, but it does have a little bit of a bass-backwards feel to it. You're going to try to appeal to D'Alembert's solution. So D'Alembert's solution says that if you could extend your initial conditions on G and H to the entire real line, then you could solve the wave equation using D'Alembert. And so the idea is that if you could solve the wave equation using D'Alembert in such a way that the initial conditions are also preserved on the boundary, when you then restrict that solution from R2 to this region, it will be a solution to the wave equation like on this boundary. And when I prove to you later on that any solution that satisfies the initial conditions must be unique, that'll be good enough to do this. So once again, the argument is extend function g and h somehow in such a way that these conditions are also satisfied when you solve the equation. Who knows if that's possible? And if you can do that, use D'Alembert. Simply take that solution on the half plane and then restrict it to this domain. And then that would be a solution to wave equation with fixed endpoints. So there are many ways to extend a function. So you might just pick one. So let's pick one. And I think the simplest extension is what you call extension by 0. So what if you did this? So what if you said, Let me just draw a picture of G. Kind of on the GX axis, and going from 0 to L. So what if we're just like plucking the guitar string? So here's the number 1, and we've got this initial condition. Yeah. And so this is certainly a valid initial condition. Well, not exactly, because it's not differentiable here, but it actually won't matter. And if you don't like that, you could smooth it out. It'd be a little harder to write the formula, but certainly smooth out the corner. So can we extend this? Well, one way to do it is by setting it equal to 0. Setting it equal to 0, you know, less than 0, setting it equal to 0, bigger than L. And then use D'Alembert's solution. Oh, and by the way, in this example, let's take h equals 0. Let's kind of go one step at a time. And you can write down the formula for this. It's just linear formula. Here it is. It's 0 for x less than or equal to 0. It's 2 over L. As you're coming up, and then as you're going back, what would it have to be? Negative reciprocal slope starting from from 2. And I'm running out of room, but after that, it's 0. So this is a piecewise defined function. It's quite simple to write down, and you can plug this into D'Alembert's solution to the wave equation. And remember that solution in this case is just g of x minus ct plus g of x plus ct, entire thing divided by 2. So you can kind of see that after the initial time, the amplitude kind of starts shrinking down by half, and then the wave is going to be splitting apart and traveling in 2 different directions. And now you can see the problem. This is not an acceptable way to find a solution to this problem with keeping the ends fixed, because what happens is if you just restrict, you just solve it on the plane with D'Alembert and then restrict, what happens is that this wave splits off and just runs away off to infinity. But that's not realistic. So when I was young, I used to play with the cord to the vacuum cleaner, right? And flick the cord, and the wave would go down and hit the vacuum and then come back. And so the wave should kind of hit the endpoint and, like, you know, come back, and there should be some interference and so on and so forth. So extension by 0 is obviously not a good choice because it allows the waves to just escape and run away to infinity. So you're going to have some kind of extension where as D'Alembert's solution is going on, you've got maybe like extra copies of the wave that are continuing to come in and go out and interfere with each other. In other words, you might start hoping that you could find a periodic solution. Okay, but now there's still many ways to extend a function so that it's periodic or has some kind of regular behavior. So let's maybe try to be a little bit more careful in thinking of like how we can extend this. So let's try to figure out what the extension has to satisfy. So let's go the other way. So let's say, let's do a thought. Oh, I shouldn't have erased that, but that's fine. So you've written it down, or you can rewind the video. So let's say that uxt solves the wave equation. Like the wave equation for the entire real line. So let's say that you've taken uxt from 0 to L and extended it to the entire real line. It solves the wave equation. And let's say that it also satisfies the boundary conditions. You know, that g of 0 equals g of L equals 0. H of 0 equals H of L equals 0. And what is it? Like for all time t, u0t equals 0, u_lt equals 0. And so from that, let us deduce what property uxt might have to figure out what kind of extension it has to be. And let's, for the moment, let's take g of x as given, and let's take h of x equals 0. So we'll solve the simpler problem first. So just wave equation with an initial condition, but no initial velocity. And well, let's see what these conditions tell us. So you know that the solution and you know that u of 0 t equals 0 and u of L t equals 0 for all time. And so what this tells us now, you can just kind of go through plugging in x equals 0. I'm getting what? That g of ct has to be equal to negative g of negative ct for all t, for all time. And c is a fixed positive constant. It's non-zero. And similarly for L, so this is telling me what? When x is equal to L, I'm going to get g of L plus ct equals minus g of L minus ct. And this tells me two things. So first, from the class, does anybody want to volunteer? This property has a name. So what do we know about G from this property? Given that this has to work for every T. Yeah, it's an odd function. You could change the variable like S equals C times T, and then you've got the definition of odd function. Sure, this is under the caveat that H is equal to 0, but we'll broach that in a moment. And G is odd, so with axis of reflection equal to 0, this is telling you G is odd with respect to the line x equals L, right? Substituting in L for 0, you can, instead of reflecting around 0, you can reflect around L, and it'll be odd with respect to that axis. And you can argue geometrically or argue algebraically, it doesn't matter. These two things, their powers combine to tell you that G is, well, it's an odd function and it's periodic with period equal to 2L. And you can just check that really quickly, because if you take G of x plus 2L, you just kind of play with the algebra, right? This is this is equal to that, which is now equal to L minus x plus L, or minus G of L minus x plus L. Substituting into this equation, right? And this is now equal to minus G of minus x, which is equal to G of x. So that's how you use those two properties, for instance, to prove that it's periodic with period 2 pi, or periodic with period 2L. Any questions or comments on that? So now, instead of like doing the whole thing again, I'll just remark, if I take G equals 0 and I take H of x given, then I'm going to just ask you to do a similar argument. It shows that H is odd and 2L periodic, which is great. So they both have to satisfy a similar initial condition. And in this case, that's your solution, right? And so you can just sort of use the initial condition now on u sub t, right? Like differentiate this, get yourself down to H, repeat the same argument that I gave for G, and it'll work out. So I'm not hiding anything of substance from you. So for both these problems, keeping the other thing 0, the condition has to be 2L periodic, and it has to be odd. But what about if I really have G and H given, but without any restrictions? Is it still the case that these two things will be 2 pi periodic? Well, if you just write down the equations that I was writing down using the full solution, you won't get that far, because instead of something being equal to 0, it'll be equal to like the other thing. That's an issue. But what you can do, well, I'm just saying that if you take G and H given and try to redo my argument, it will not be successful because of another term here. Yeah. And that might make you frustrated because right now, strictly speaking, we've only proven this periodicity in kind of a narrow circumstance. But because the wave equation is linear, this proof is enough to prove that even if G and H are given, they'll still have to be periodic. And so what's the proof of that? So you can consider, it's a cool trick for linearity. So you can consider like 1/2 u with H equals 0. All right, G equals G to mean that G is a given function. And you can consider 1/2 u with H given and G equals 0. And these both satisfy the wave equation, say. So if they both satisfied the wave equation and preserved their initial conditions, with the d'Alembert solution, then you know that this one's periodic and you know that that one's periodic. But now if you add them together, honest to goodness, just add them together and add their initial conditions together, you get this problem that satisfies the wave equation. Because the wave equation is linear, L of 1/2 u plus L of 1/2 u is equal to LU. If it were not linear, then this argument would not work. So we kind of landed on the idea that the extension of H and G should be odd and periodic with period 2L. And that's kind of cool. So like if you want to go back and look at this initial condition I drew before, and now if you want to draw the odd extension, it looks like, let's take L, 2L, 3L. So on and so forth. So you get that sawtooth function. So of course, that's what it looks like. So that's the function. We've proved that if we use D'Alembert's solution for this extended function, and if it satisfies the initial conditions, you know, for the wave equation just on 0 to L, then when we restrict back, and if it's true that we get a solution to, you know, the wave equation from 0 to L, then it has to come from this periodic extension. So now what you would do now is like test it. You would test it and see if you actually get a physically realistic solution. So you take the formula that I wrote before and just kind of repeat it on each section. And then you can find out a formula for what the solution looks like just from this interval from 0 to L. And I worked out a few, you know, time slices myself before coming to class, but it's not going to be useful for me to work that out. In front of you, what I will do is I've got this little movie player that can show it. If you want to join the Zoom call, you can see it with me. Otherwise, you can click on the Google Classroom. And you can see it. Or you can just watch the video later. Hopefully it won't take me too long to get this set up, but you can kind of see what's going on. So let me share my screen. So this is like from the site academia.org, and I'll put the initial condition as 2 moving Gaussian pulses, but that's the closest situation to kind of what I've got on the board. And so it's now fixed endpoints, and so I'll show you the animation. So you can see the waves canceling each other out and then like switching positions, and you can see when they get to the endpoints, the physics of it makes the waves switch from, you know, positive position to negative position. And got some people in the waiting room. Perfect. Okay, so yeah, there it is. And that switching from positive to negative is why it is required that we have this odd extension, so we can get like the negative inputs, you know, because D'Alembert makes you slide off to infinity, but if you're periodic for all time and eternity, then sliding off to infinity just introduces you back to the other side. And then you get all this, cool stuff. So hopefully that worked out for the YouTube video. We'll stop sharing now and go back to it. And actually, I think we're kind of close enough to the end that I'll just oh, I see. I cut off my video by accident. Yeah, I think we're kind of close enough to the end that I don't want to get into the next topic, which goes by Duhamel's principle. If you're familiar with distributions, it's just saying that you can solve an equation with a forcing term by using convolution. But of course, you don't have to be familiar with that yet. We'll go at it from the ground up. So next class period will be solving wave equation equal to a forcing term using Duhamel's principle. And we do have to do some multivariable calculus to get that going. So definitely recommend that you pre-read. So what I'll do is for the people physically in the room, take the next couple of minutes. We could chat about the homework if you like. Otherwise, I think I've gone over enough that it's okay to end early. So I'll just say thank you, everybody, and I'll see you next time.